The sense of hearing is sometimes simply referred to as our sense of audition. And when you think about our ability to hear as humans, it's remarkable. We can detect a wide range of sounds. We do have a little idiosyncrasy here where we respond best to frequencies that are in the range of the human voice. Now, some people, hearing is like everything else that we encounter. Some people are much more sensitive to certain faint sounds. Others, could not hear the loudest of bangs going on. That goes back to what we talked about with regard to absolute thresholds earlier in the slideshow. Part of that survival mechanism is the idea that we need to hear. If you go back to animals roaming in the wilderness and anywhere else, you talk about we need to hear if somebody is approaching us. But it can't be too sensitive. It would be a situation where if we heard everything, we would literally hear ants marching around. It would be like a Dave Matthews concert. The other thing is we have a tremendous ability to distinguish between voices. There existed a time before caller ID that when somebody called your house, uh, you didn't know who it was. You had to run the risk of picking up that phone and saying hello, not knowing who was on the other end. And oftentimes you would get the person who would say, "Hey, it's me." Remarkably, you would know who it was because we have that unique ability to distinguish between voices as well. Now, how do we hear? It's air molecules. And the air molecules are colliding together. And if you've ever seen a ripple of water going through a pond, a puddle, a pool, whatever it might be, if you drop a rock or something into it, you know that it radiates out. That's exactly what the air molecules do. One collides with one, which collides with others, and it becomes a real snowball kind of effect. And what happens is we pick up on that change in air pressure. Those air molecules and the change in air pressure channeled into the ear, and it is transduced. There's our translation term, but it's transduced into those neural impulses, and the auditory cortex on the temporal lobe reads that image and tells us what it is that we're hearing. And our sound, our sense of sound and audition is remarkable. Now I'm going to bring in this video here. Watch it. This young man, he makes me laugh. But what comes out of this is that you learn a little bit about how sound works and the impact of the vibration of the sound molecules. Um, it's remarkable what the human ear is capable of. Now, as we move on, again, please make sure you watch that video. It's short, it's 5 minutes. Do it on your own time, but you start to see it highlights a little bit in there about sound waves. And if you look at this, this comes back to where we talked about, uh, you know, visible light spectrum and wavelengths of light. Wavelength of sound is super important as well. And just as it says here, the shorter the wavelength, the higher the number of frequency that we are going to see in a given period. And therefore, the higher the pitch will be. So if you look at the bottom here and you look at these two wavelengths, the top one has a much shorter wavelength. So therefore, in the same period of time, let's take here to here, look at how many more wavelengths we experience in the top one versus the bottom. So that is all about how high the pitch is that we are going to sense, or vice versa, how low it is. Now, the amplitude or the height of the wave is going to determine how loud the sound is going to be, or how soft it's going to be. So the taller the wave, the louder the sound, and vice versa. So again, waves, whether it's light energy or whether it is going to be air molecules, it is going to determine what we experience after we gather those senses. Now, how are they measured? They're measured in decibel ratings. A small d, capital B is going to be the abbreviation. If you talk about the absolute threshold for hearing, if you remember when we went back to the ticking of the watch in the quiet room, it is 0 decibels. That is our absolute threshold. Now, everything else is going to be rated against that. When you talk about decibel ratings for some familiar sounds here, uh, a shotgun blast, very loud sound, is going to be about 140 decibels. Again, I'm just learning how to use a computer here, so bear with me. okay, about 140 decibels. 120 decibels for one of those loud banging claps of thunder. If you've ever been down near a subway when it goes screeching by, it's at about 100 decibels. A normal conversation that you would be carrying on with somebody, about 60 decibels. A whisper, about 20 decibels. And then ultimately down to that absolute threshold. Now, if you've ever gone by and you've seen landscapers outside working on their lawns, or if you've seen air traffic controllers, they usually have headsets on, covering their ears or earplugs of some sort. They are designed to reduce the amount of noise and thus limit the amount of damage that could potentially occur to the ears. Usually they're rated at what's about a 30 or so decibel rating. So you can see that what they end up doing is reducing the sound to a little more than a whisper, but less than a normal conversation. So it's really remarkable what they're able to do. And they do, in fact, preserve your ears as you age. Because what we're going to see in a minute is how our hearing gets damaged. Now, the function of the ear is one thing, but let's look at the basic structure. It's divided into three parts, really: an outer, a middle, and an inner ear. The outer ear, which is our visible portion, that's what you see on people, what many people will pierce, is called the auricle or the pinna. It's mostly visually pleasing or not, and that's basically its real function. What we really need in order to hear effectively is the middle and inner portions of the ear. Okay, primarily what the pinna or the auricle is doing is channeling those sound waves into our auditory canal. That's where the real sound is going to occur. So the shape of the ear is going to allow more or less in the way of the air molecules to be channeled into that region. Now, as we work our way into the middle ear, we get to the original portion called the eardrum, which is a very tightly wrapped area, just like the surface of a drum in a percussion section of a band. And what happens is, as the eardrum starts to vibrate, we end up seeing the activation of three little tiny bones in the middle ear. And they are called the malleus, the incus, and the stapes. Now, oftentimes, especially on the AP, you'll see them referenced not by the technical names, but either as the hammer, the anvil, or the stirrup. So I would just be familiar with both sets of terms. And then ultimately, the air molecules are channeled and work their way to a portion of our inner ear called the cochlea, which is, if you have ever seen a graphic, it is a snail-shaped like tube that is on the inner ear. And we're going to see exactly how that works in a minute. Now, on the inner ear, what happens? The incoming vibrations, once it passes through the eardrum to the malleus, incus, and the stapes, works its way to the cochlea. There is actually a fluid in the cochlea. And what happens is you'll start to see little motion and little ripple effect of the fluid that is in there. And what happens is there are tiny little microscopic hair cells in this region. Now, these hair cells are not visible to us. I know people think right away, oh, it's disgusting, hair in the ears, whatever the case may be. That it's not visible. It's microscopic. And it's all the way buried in that inner ear. And what happens is, as the fluid moves, these hair cells actually start to bend a little bit. Kind of like the scene in The Matrix, where he's falling backwards. And as they bend, they start to kind of knock into adjacent nerve fibers and send messages off to the brain. And this activates really how we're going to hear. And what it does is it determines, based on the number of hair cells that are being activated, how loud a sound is that we're actually going to hear. Now, that's how loud something is. How is the pitch determined? The pitch is going to be determined based on who you ask by one or two different theories. And sometimes one of them works really well. Sometimes both theories are needed to explain how pitch is determined. Based on where in the cochlea the hair cells have been activated, this is called the place theory. That will tell you how loud and exactly how many sounds people have been exposed to over the years. So somebody who works in a job where maybe they're more likely to be around loud sounds than somebody else, they may have a much different activation level. Now, how is this confirmed? They will slice into cochleas of cadavers, and they will actually, as gross as that sounds, they will actually have the ability to determine it this way. This does a really good job of explaining the high pitches. Now, again, one theory doesn't always do it, so we often need the complementary theory of something called the frequency theory. Now, the frequency theory will allow us to really do a better job of explaining those lower pitch sounds. And how does this work? It's right here. The vibration is going to trigger neural impulses at the same rate that we see this vibration going on. So what happens is the brain starts to interpret what pitch is going on by the frequency of the neural impulses. So again, both theories are really needed. It's kind of like with color vision, how we saw both the trichromatic and the opponent process theory were needed to explain things. It's very similar here as well. Now, we talked about how we hear. Well, how do we lose our hearing? There's really three main ways. The first one is called conduction deafness. If there is a poor transfer of sounds from the eardrum to the inner ear. Oftentimes a hearing aid is used here. It's able to kind of bypass the area where there is a poor transfer, and they can address the issue. Second one is called sensory neural deafness, and this is when the hair cells are damaged, or when the auditory nerve itself, which is helping to take this off to the brain, is damaged. This happens in one of two ways. Either by age, as we get older, we often struggle a little bit to hear sounds. Well, what's this caused by? Repeated damage over time. Now, some people, oftentimes students will be sitting in classroom and you can hear their headphones from across the way. That is a loud noise that is probably damaging their hair cells. And the problem is these never regenerate. And hearing aids are often of very little help here. And finally, we have something called stimulation deafness. This is very loud sounds. Now, this is very similar to sensory neural, but it's usually from a single loud sound. Somebody who has a gun fired off very close to them could end up damaging that portion. So very similar to sensory neural. Now, if you check out this video here, what'll come up here is hearing aids, how they work. It's remarkable what they're able to do. You see a visual like this video over here. Please check it out also while you're on here. A boy who had no ability to hear and hears his father's voice for the first time after a hearing aid. They're really remarkable. So check some of these things out, please, on your own time. Now, as we talk about this second video here is one I would go to, except for the fact that it's not loading on my computer either. I was hoping it would work for you. It was one of the videos that was linked to that other one about a new type of digital hearing aid and how microscopic some of these advances are now. A lot of people, for vanity reasons, will not wear a hearing aid and will actually go unable to hear because they don't want the hearing aid to be visible to other people. So it talks about just how small they're making them now. Okay. Now, that's going to wrap it on hearing, and we're going to move on to touch. But hopefully I'll be back for you to address that. Have a good one.